All right, let's finish this problem off. Yes, I am recording. So if we take a look at the momentum in the x direction, we get mass of 1 times 5, and that's the only momentum before the collision. On the other hand, we have m1 v1 b cos 30 plus m2 v2b cos theta. Of course, all of the masses are the same, so mass 1, mass 2 all cancels out. And actually, there are 1, 2, 3 unknowns in this equation. 3. That is a lot. In the y direction. Before the collision, there is no momentum in the y direction, so that's a 0. After the collision, we have v1b sine 30 equals, not equals, minus v2b sine theta. Again, technically there's an m1 and m2 in there, but they're the same, so they're going to cancel off. And that tells us that v1b sine 30 has to be equal to v2b sine theta. So again, 3 unknowns. We've written down 2 equations that both have 3 unknowns in them. v1b, v2b, and theta are all unknown. So if we want to solve for 3 unknowns, how many equations do we have to write down? Yeah, we got to have a third equation. Fortunately, we have that, because billiard balls make elastic collisions. So because they make an elastic collision, we also have the energy at A equals the energy at B. So that means, so the only kind of energy that we have here is kinetic energy. We're not, at A and B, there's no spring deformation, there's no change in height, there's no any other weird thing going on. It's just kinetic energy. So we have 1/2 m1 v1a squared equals 1/2 m1 v1b squared plus 1/2 m2 v2b squared. That's right, spring forces would only be during the collision, which we are not directly looking at. We're only looking at just before and just after, but not during. So once again, all the masses cancel out. And this is actually kind of fortunate. We only have 2 unknowns in this equation. We just have v1b and v2b. So we can have something like v2b squared. Oh, all the halves can cancel out as well. So v2b squared equals v1a squared, which is 25, minus v1b squared. And we can just go ahead and take the square root of both sides. We get an expression for v2b in terms of v1b.
So where's the 25 from again?
So v1a is 5. So 5 squared is 25.
Thank you.
Hmm? No plus or minus. No. So here, the plus or minus is going to be added based on direction, right? And we already know that that ball 2 is going to the right and down, so we know the direction. So we don't bother with the minus sign, right? Because the minus sign in this case, if we put a minus sign on v2b, that would mean that our ball is actually traveling up and to the left, and that doesn't make any sense. So mathematically, the minus sign is a possibility, but physically we discard it because the plus sign is the one that makes sense. Now we plug this into that's exactly right. We can plug this into the second green equation from the y direction. We're running out of room on this page though, so I'm going to copy over a bit. Oops. If I can get this to cooperate. No cooperation. That's fine. Give me just 1 second to organize this. All right. So here's the 3 pieces of information that we learned by doing a momentum analysis and an energy analysis. We are, at this point, done with physics. All our physics is done. It is just time for math, which I know is everybody's favorite part, so we're not going to skip it. So we'll label these equations 1, 2, and 3. If we take 1 and plug it into 2, we get v1b sine 30 equals square root of 25 minus v1b squared sine theta. Let's solve for v1b here. So we're going to square both sides. So we get v1b squared sine squared 30 equals 25 minus v1b squared sine squared theta. We want to put all the v1b's on the left-hand side. Everything without a v1b can stay on the right-hand side. So we take this minus v1b squared sine squared theta term, add it to the left-hand side, and we can factor out a v1b squared.
Can you repeat what you did in the step before this to isolate the v squared b?
So on the right-hand side, we did a little distribution. So we get 25 sine squared theta minus v1b squared sine squared theta. And then this term, we add this term to both sides to get it over to the left. And then we factor out a v1b squared.
Got it. Thank you.
Okay. Okay, so messy but still doable. What do we do next? Who has an idea?
We can plug that into the first equation, get v2b.
We could get v2b in terms of sine theta. That's true. Or we could plug it straight into equation 3. Also true. We've got a couple votes for plug it into equation 1. And yeah, this right side should be under a radical. You are absolutely correct. So this is 1 into 2. So yeah, we could totally take 4, plug it into 1. Oh, horrible. It's not horrible. Let's not exaggerate. Come now. v2b equals square root of 25 minus 25 sine squared theta over sine squared 30 plus sine squared theta. And actually, we've got a 25 in both terms here, so I'd like to factor out the 25. And then square root of 25 is 5. So we can just say v2b is equal to 5 square root of 1 minus. And sine 30 is what? Sine 30 is a half. So sine squared 30 is a fourth. There we go. Now, this is harder than what you'll get on the exam, but you don't practice for a competition by, you don't practice easier than the competition, right?
This is a math question.
Yeah.
A square root inside a square root would cancel?
No, but if you look at equation 1, v1b is squared. So the square and the square root cancel.
Ah, got you.
And then there's just the outer square root. All right, and then last, we can take this blue equation and this red equation, plug them both into equation 3. So we can get 5 equals 5 square root of sine squared theta over 1/4 plus sine squared theta. All of that times cosine 30 plus 5 times the square root of 1 minus and then times cosine theta. Okay, so we're actually in a good spot here. We only have thetas. Right? There are only thetas in this equation, so it's solvable. Right? In fact, so let's cancel off all these 5s, like so. What I'd like to do is take this first term, subtract it to, well, how do we want to take care of this now?
May I ask a question? Because I just lost you at this last part. So where did you plug the V2B? Which equation?
So this V2b went here, and this V1b went here.
Got you. Thank you. I'm just moving the little wheel so that I see what's before that.
Are we free to square everything?
Yeah, we can square everything. Let's see where that takes us. So 1 equals, on the right-hand side, we have 2 terms. So when we square, we're going to get first term squared plus second term squared plus twice the product. So first term squared will be sine squared theta over times cosine squared 30. Second term squared will be 1 minus sine squared theta all times cosine squared theta. And now comes the cross term. Plus 2. I'm definitely going to run out of room. Let's finish this up on a new board. all of that square rooted still, and then cos 30 cos theta.
I have a quick question.
Mhm.
Where did that one on the left-hand side come from? I thought equation 3 was just 5 equals to v1b cos to 30 plus
You
v2b cos of
you are correct. There was a 5 over there, but there was also a 5 in both of the other terms on the right-hand side, so we just divided everything by 5.
Oh, okay, okay.
So, I will say a couple of things. Firstly, this does look ugly. Part of the reason it looks so ugly is because of the choice we made about what order to do the algebra in. A lot of steps for one problem. Yeah, you're not wrong. You love this? I absolutely love this. Easy to lose track with all the symbols. Also true. How do we pick the equations in? That is the million-dollar question. Let's go back a few steps. Actually, this will work. So we start with equation 1, 2, and 3, right? Choosing a way to start off with these, that is in fact the million-dollar question. Like, if you, it's not always obvious what the right way is. He did this on purpose. Yes. Yes, I did. You will definitely see a variation of this problem again. I purposefully made it difficult by making the angle on velocity b unknown. So let's actually let's go back. There. This angle being unknown is what makes this hard. If I had made one of the other things unknown instead, it would have been much easier. What I wanted to illustrate here is that so it's not always easy to know when you've chosen to solve in the right order. But it's frequently easier to know when you've chosen the wrong order. If you get something like this, you have chosen the wrong order. No, it's not supposed to look that way. If you get something like this, this statement that we've written here in purple, this is a technically correct statement. It's technically correct. And yet. Could we go back and solve it in the right order? No, we're here. We have to finish it now, right? There are some standard tricks to make this look better in a hurry. The number one thing that makes this equation look terrible is that there are fractions. So the first thing what we're going to do is we're going to multiply everything by 1/4 plus sine squared theta. That's going to get rid of all the fractions. And yeah, maybe we'll compute cosine of 30. So cosine of 30 is square root of 3 over 2. So cosine squared of 30 is 3/4. Right, so this term comes from this term after we've multiplied off that denominator. These next two terms both come from this term after we've multiplied by 1/4 plus sine squared theta and distributed that cosine squared theta. And then we have to be a little bit careful with this thing in parentheses. So we are multiplying by a factor of 1/4 plus sine squared theta. When we move that into the square root, we're going to get the square of 1/4 plus sine squared theta. One of those factors is going to go to cancel this denominator here. One of those factors will be used to cancel the denominator in the second factor, in the second term of the second factor over here. So what we will get, we'll get 2 Okay. This looks a little better, right? A little. And there's some cancellation that we can do. We have a minus sine squared theta cosine squared theta here. From these two terms here, we're going to have a positive sine squared cosine squared. So actually those cancel. And then let's work on this thing in the radical a little bit too. We can factor a sine squared theta out of both of these terms underneath the radical. So we could pull one of those out. And when we do that, something magical happens underneath that square root. We're left with a positive sine squared theta and a minus sine squared theta. Boom. Gone. So the only thing left inside this square root is a fourth. And square root of a fourth is a half.
Isn't the square root of a fourth a 16th?
No, the square of a fourth is a 16th. Right? But a half times a half is a fourth. So we know the...
Oh, yeah.
All right. So let's... now with these cancellations that we've done, let's write it down again. So we have on the left-hand side still 1/4 plus sine squared theta equals 3/4 of a sine squared theta plus 1/4 of a cosine squared theta plus, and then we will just have a sine theta, cosine theta, and a cosine of 30 is square root of 3/2. So
Wait, I'm confused. We have a plus sine squared theta cosine squared theta minus sine squared theta cosine squared theta. Why doesn't it get rid of the first cosine squared theta?
you mean this part that I've marked in pink here?
Yeah.
So
Cosine squared theta that doesn't have a pink line through it.
right, because that cosine squared theta is still going to distribute onto the fourth. So when we do the distribution, we get a fourth cosine squared plus sine squared cosine squared, and then minus sine squared cosine squared.
Right. Okay.
Are we gonna put the 2 next to the sine theta, or do you like cancel out the 2 somewhere?
Yeah, so we had this 2 here, but then we also had square root of a fourth left here. And so square root of a fourth is a half, so the 2 and the half canceled off.
Okay, thank you.
All right, starting to look a lot better, right? You just keep saying that when it's not, it's always bad. All right. You guys. Does anyone remember what my favorite website is?
Wikipedia.
Absolutely Wikipedia. Yes. The reason why I ask, because if we simplify this a little bit more, right? And something that I'd like to do, what I want to do is subtract this sine squared theta from both sides. So that actually gives us 1/4 on the left side equals, and now we have a 3/4 sine squared theta minus a sine squared theta. So that's going to give us minus a fourth sine squared theta. So I'm going to factor the fourth out from both of these first two terms. And so I mentioned Wikipedia, so because it seems like, to me, it seems like, man, that really looks like a trig identity, doesn't it? Isn't there some trig identity there? Isn't it minus a fourth? Yeah, it's minus a fourth. That's where the minus sign here came from. So if it was cosine squared plus sine squared, that would be 1. That would be way too convenient, right? We know that we know by this point in this problem, we are not that lucky. But there is a nice trig identity for it. So we go to Wikipedia and we go list of trigonometric identities, or more likely we all use our bookmark because everybody has bookmarked that page by this point, right? We scroll down and we say, oh, wait a minute, actually cosine squared minus sine squared is cosine 2 theta. So this thing here, this is cosine 2 theta. And while we're looking that up, we notice right next to it, actually sine theta cosine theta is also an identity. This is 1/2 sine 2 theta. So let's rewrite. 1/4 equals 1/4 cosine of 2 theta plus 1/2 square root 3 over 2 sine 2 theta.
Can we multiply everything by 2 to get rid of that half?
Yeah, in fact, let's multiply everything by 4. So 1 equals cosine 2 theta plus square root of 6 sine 2 theta. So by now it's actually looking okay, right? Yeah, square root of 6. So we multiply by 4. So we get 4 divided by 2 divided by square root of 2. That leaves us with just a square root of 2 in the denominator. So square root of 2 times square root of 3 is square root of 6. This is still not easy. If we had a 0 on the left-hand side, then it would be great. We would just say, oh, well, yeah, that's 0. If 0 equals cosine 2 theta plus sine 2 theta, we subtract one of them to the other side. We divide by cosine 2 theta. We get a number equals tangent 2 theta. We solve. Boom. But the fact that there is a number there, now it makes it a little more challenging. Do not lose hope. If all is lost, right? This is actually simple enough that we could just go over to Desmos, graph this son of a gun, and see where cosine 2 theta plus square root of 6 sine 2 theta equals 1. In fact, everybody's familiar with Desmos, right? Has anyone not used Desmos before? let's use Desmos together, since we are here. So there's our right-hand side. There's our left-hand side, and we just have to look where they intersect. So two possibilities. The first possibility is that actually the angle is 0, which means that ball 2 just goes in the x direction and there's no movement in the y direction at all. That wouldn't help us make our billiard shot, though. So probably it's this other one over here. So our angle would be 1.183 radians. Why did I choose that peak? There are infinite peaks, but only one of them makes physical sense. Right? So this first peak is if our ball just went straight in the x direction. We already know that's not happening. It's going down and to the right. So our next possibility is 1.183, which is what? It's like something like pi over 3. So that works. And then our next possibility is pi, which means that actually our ball would be going in the left direction. So if our cue ball comes in from the left, hits a ball, that ball is not going to go to the left. So we throw that point out. Right? So we're able to see which intersection it would have to be just based on what quadrant we know the ball 2's direction has to be moving in. Right? We know that the movement has to be going in the fourth quadrant, but this is like first quadrant, fourth quadrant, third quadrant, second quadrant. Only one of those is a possibility. Now this is a last ditch thing. If you can't figure, if your math skills completely fail you, you always have Desmos. But I don't think we're out of tricks yet. Because we can take this equation, we can reorganize it one more time. This cosine 2 theta, I want to subtract it to the left.
Dr. Wolf, we can't see your screen.
You can't see sketchbook?
No, it's just a blank page.
Let me try again. Alright, don't crash on me, WebEx. I know we shared Chrome. Don't let that intimidate you. Can anyone hear me?
Hear you, but we can't see you. There's a little triangle that says, I don't know, local computer conditions or whatever.
Yep, because my WebEx is freezing. WebEx doesn't like it when I share Chrome. So I will be right back. Don't anyone go away. All right, I'm back. About 50% of the time I try to share a Chrome browser, my WebEx crashes. Yeah, Cisco really wants you to integrate with Microsoft products. Um, so, like, WebEx is more than happy to export your appointments to your calendar as long as it's an Outlook calendar. So maybe they are just mad that I'm not using a Microsoft browser. Anyway, can everyone see my sketchpad now?
Yeah.
Okay. So we rewrite our last equation just a little bit, and we use one more trig identity. Because this thing here on the left-hand side, this is also a trig identity. Now, you know what? We're not going to go there. We've spent enough time on this problem. I think I've made my point about using Wikipedia to look up trig identities and order of solving making a big difference. So we just say we went to Desmos and we got our options were theta equals 0, theta equals 1.18. Right, so if we look at our picture, right, this is what direction is ball 2 moving in. If 0 was our solution, then that would mean it's moving in that direction. If theta is 1.18, it's moving in that direction. And that right there is what we originally drew. It's after the collision, our second ball is moving into the fourth quadrant, an angle of theta below the x-axis.
I have a question. For the correct way to solve this problem, would that be to get rid of the fractions first and then to square everything?
It's always going. So the squaring part was always going to be messy because there was a constant term, right? That didn't have a square root in it. So it was always going to be messy.
We also, Desmos was giving us radians, right? When we were dealing with degrees before.
Yep. So Desmos works in radians, so we have to convert. Oh, and also this is not just theta. This is 2 theta, right? So 2 theta is equal to these things. So 1.18 radians is how many degrees? Anyone know? Maybe you can. I don't usually bother doing that. So this is 1.18 radians is about 67 degrees. So that means our theta is half that, so it's like 34 degrees.
How did you know that solution was in the fourth quadrant and not the first quadrant?
From our original drawing. So
Yeah,
the
but I mean, 1.18 radians, because when you draw a circle, isn't it positive? Wouldn't it have to be negative 1.18 radians
that's a
for it
good
to be?
that is a good question. The way we drew our picture though is that the angle actually defined how much into the fourth quadrant we were. Right? So it's the
Oh,
angle below
okay.
the x-axis.
Okay, thank you.
Yeah. All right. Now that we've got the angle, like most of the work is done. Right? We can take this equation in blue we have right here, right? And now that we have the angle, we can just say, well, V2B is equal to 5 times 1 minus sine squared of 34 over 1/4 plus sine squared of 34. So this fraction under the radical here is like 0.55. So 1 minus that is like 0.45. So our V2B is about 2.25. We can do the same thing for V1B down here. Since we have V1B also only in terms of theta, again, this thing here is about 0.55. That's the same thing we have under the radical for V1B. So we're going to have 2.75. So these two numbers here are magnitudes. And once we go back to our original here, we can say, well, okay, then V2B is, in vector form, it's going to be 2.25 times cosine 34 minus 2.25 sine 34.
That's cosine 34, right? Not 45.
Yep. And the same for V1B. So V1B vector form is 2.75 cosine 30 in the x direction, 2.75 sine 30 in the x direction, in the y direction. All right, so this problem is obviously way more complicated than anything you're going to see in the exam, and it's probably harder than any of the textbook questions as well. But we managed to hit all of the high points of momentum conservation, right? It's conserved separately in the x and y directions, and sometimes energy is conserved as well. Right? That's basically all of the concepts from the momentum chapter. we got to practice a genuinely difficult system of equations, which is something we don't have the chance to do a lot. And we got to remember that there are many trigonometric identities, most of which we will never remember what they are, but if we just remember they exist, we can look them up.